Hey dear decision scientist, let's do another category of network models, the third category. So far, we have done two categories, supply chain models, including transportation models and transshipment models. And also, in the last session, we did together assignment problem. Today, we are going to do shortest route problem, the third section in chapter 3. Maybe 10 years ago, 20 years ago, 30 years ago, the concept of shortest route problem was to some extent confusing. That what does it mean, shortest route problem? But now it is one of the easiest one in terms of understanding because we use this model in our everyday life. No matter we are walking, biking, or driving. Shortest route problem is the base of GPS navigation systems that has a huge involvement in our everyday life. So, when you are driving your car to a new destination, you put the destination, and according to your current position and the destination you have put over there, the GPS system in your car suggests several routes that connect the origin to the destination. What is the measure for do that? Shortest distance, fastest distance, cheapest distance, and all these things. Now, with the example that we are going to do quickly together, you will understand the math behind this model much better. But let's review this description here together, and with the first example that I told you, or first introduction that I gave you, you should have a good grasp of the concept after reading this slide together. Okay, it says the shortest route problem is concerned with finding the shortest path in a network. Why it is network? Because of course, when you are checking a map of your city, there are many intersections, there are many roads, there are many highways, and if you consider roads, highways, freeways as arcs, the points that connect the beginning and end of each arc, each road, each highway is considered a node, for example, an intersection. If all arcs in the network have non-negative values, that is exactly the case that we have in our GPS system, because it is a model that all the values on the arcs are non-negative, are in fact positive, because we don't have a road of short 0, because when a road shows on a map, it is at least has a length of, for example, 10 feet. So we are ready to apply this model for navigation system, because as you can see, we are meeting one of the requirements for using these models, that is the values associated to the arcs must be non-negative, and the values associated to the arcs in our case is the length of that arc, that is the length of that route between two specific nodes. We are gonna do a very good case together, and you will have a much better understanding of this case. The criterion to be minimized in the shortest route problem is not limited to distance, even though the term shortest is used in describing the procedure, because the first time that when they start development of such models, they focus on minimizing the distance. But now these models are used to minimize the cost of transportation, the cost of move. They are used to make the time of transportation minimize. As you can see with your GPS system, sometimes when there is a toll on a highway, for example, or on a freeway, they always gives you alarm that it is not the cheapest way that you can get to that place, because you need to pay, for example, for that toll booth, if I'm correct with the word. Okay, so let's start a case, a typical shortest route problem. It is something that we all can identify ourselves with. You see, node 1, it says government's office. And here we have 6, that is the destination. We can consider that it is government's home. Okay, now it is on the map. It is a street, for example. It is a highway from government's office. It is exactly as what you are seeing with your GPS. There are roads, they are placed that different roads are connected. For example, intersections, or the places that you need to change the road. For example, maybe this is a highway. It is a highway of, for example, 30 miles, 40 miles, but from 1 to 2 is just 10 miles of that highway. And after that, you need to change your path to another highway, to another road, to another freeway. And now it says from 1 to 2 is 25 miles. And here it says the length of each arc is not necessarily proportional to the travel distance it represents. So do not consider it as a scaled graph, because you see it is 25 miles, it is 3, they are in the graph of the same length. So it is some sort of disclaimer. Again, I'm not sure with the word, but it says that things that you see in front of you. All roads are two-way, thus flow may be in either direction. So that's the reason none of the arcs that we see in the graph in front of us are not directed, because the same way you can go from 1 to 2, you can go from 2 to 1. So now we have this map in front of us, and we want to find the best way, that is the shortest distance way from 1 to 6. Let's see how we can apply distribution models for these things. I'm sure you agree with me that it is a network we see in front of us, because as you remember, for the network we have many origin and destination. Here from 1 to 2 is 1 works as origin and 2 as destination. 2, 3, 2 is origin, 3 is destination. 3, 5, 5 is destination, 3 is origin. And here 3 is destination of 1. So you see many nodes, many arcs. So it is called a network. And when you are working with network, you must specify from where to where. So, but here the values are fixed, my friends, because the values are distance. So we will see some other problems that in the following sections, that you must specify from where to where with what value, like the previous ones that we had, because the previous transportation models that we had, it says from which city to what city, how many generators must be transported. But here since the length of the path is fixed and it is for sure, says here you need to change the path of 1 2 to 1 of 2 6 2 4 and 2 3. So we just need to specify from where to where, and it would make it easier. Okay, we are gonna do a mathematical model over this to solve the problem that which route must be taken to get to the destination. Here, my friends, it says all roads are two-way. Thus, flow may be in either direction. But here, since it wants to make it more educational, it shows you the direction of the arcs as well. So these two things are exactly the same. Let's compare these two things together. I stopped the video here. So in fact, you should pause the video and check what is the difference between these two graphs that you see in front of you before I explain more over them. As you notice, they are completely the same except the direction of the arcs. But usually the first question that comes to the mind of students is that why, if all of them are two-way streets, why the route 1 2 is single direction? Why the road 1 3 is single direction? Why the roads 2 6, 4 6, and 5 6 are single direction? The reason for that has something to do with the fact that 1 2 and 1 3 are the routes from the origin node, and the roads 2 6, 4 6, and 5 6 are into the destination node. It means that it doesn't make sense that we have or we consider routes from 2 to 1 because 1 is the origin node and we want to go away from 1 and there is no need to return back to that point. So in that way you are making your model easier and you are telling your computer and you are specifying on the mathematical model that you are making on the paper that only go away from 1 from 1, and for the other way, for the other node that is destination node, for 2 6 4 6 5 6, since your goal is to get to the 6, you must not get away from 6, and as soon as you get to the node 6, it is the end of journey. So that's the reason we don't have any route from 6 to 2, 6 to 4, 6 to 5, although all these roads are two-way, but we are specifying for the mathematical model, or we are telling the computer, do not consider getting away from 6. As soon as you get to the 6, stop over there. That's the end of journey. For the 1, never go back to 1. Always get away from 1 to the other parts. It's something like, for example, non-negativity constraint that you are telling, never give me negative number. They don't make sense. And here exactly the same thing. Returning to the origin doesn't make sense, or getting away from destination when you get to the destination doesn't make sense. So with all this information that now you have about this problem, we can start making the mathematical models with several activities according to the good foundation of mathematical modeling that you have. I'm asking you question, you pause the video, you write the answer, and after that you check your answer.